Something emerged from behind the sun, and the silence that followed is louder than any signal. On a NASA server sit the sharpest images ever taken of a visitor from another star. The target is 3I Atlas, already breaking rules for comets. Those images were captured over 40 days ago. Instead of open data, there is nothing, no public release and no technical note. Yet routine Mars photos keep flowing as if nothing is wrong. So stay with me, like this video, and subscribe, because this quiet delay might be the strangest part of the story. To understand why this gap matters, we need to rewind to the start of October. On the 2nd and 3rd of that month in 2025, 3I Atlas drifted to within about 29 million kilometers of Mars. That is close enough that the Mars Reconnaissance Orbiter, a spacecraft already circling the red planet, could swing its most powerful camera toward the passing visitor. The HiRISE instrument is legendary among planetary scientists. It normally picks out boulders, sand dunes, and rover tracks on the Martian surface. Pointed at an interstellar object, it should deliver the clearest close-up views humanity has ever had of anything from another star. From that distance, the camera can resolve features down to tens of kilometers across. And because Mars sits off to the side of the Sun from our point of view, the geometry is perfect. While telescopes near Earth see 3I Atlas almost backlit by solar glare, HiRISE sees it from a different angle, a side view. That means those hidden frames should not just show a fuzzy blob and a tail. They should reveal structure, the true size and shape of the core, how many jets are firing, whether that strange sunward pointing material really is a single anti-tail or something more complex. In other words, those images are not just pretty pictures, they are a missing piece of the puzzle. If you are trying to understand whether this thing is a hyperactive comet or something stranger, you want every possible viewpoint. You want to see how the jets are arranged in 3 dimensions, how far they extend, whether they fan out or stay tight like beams. HiRISE had the chance to catch all of that at the exact moment when 3I Atlas was heading toward its most dramatic encounter with the Sunday. So where are the results? This is where the story takes a bureaucratic turn. The HiRISE team continues to post new images of Mars itself. Day after day, fresh shots of craters and dust avalanches and layered rocks appear on the public website. The pipeline is alive and healthy. The servers work. The software works. The outreach channels are functioning. Yet when you search for 3I Atlas, you hit a wall. Instead of a clean download link, you find a notice that any images of this interstellar comet are classified as NASA-wide news. During the federal government shutdown, that label came with an explanation. Official news communications were suspended, the notice said, so anything marked as NASA-wide news could not be released yet. At first, that sounds dull and almost comforting. A simple paperwork issue, the kind of thing you shrug at and expect to clear up in a week or two. Except the shutdown ended. Other NASA announcements resumed. Press releases went out about rockets and weather satellites and Mars geology. Still, nothing about 3I Atlas. Those HiRISE frames stayed locked behind that same banner. Meanwhile, outside that firewall, the scientific clock kept ticking. 3I Atlas swung through perihelion, its closest passage by the Sun, on the 29th of October. Ground-based telescopes watched it brighten and change in real time. Some observatories recorded multiple jets. Others saw a vast glowing halo surrounding the object, stretching hundreds of thousands of kilometers across space. Every new observation raised new questions. Was the nucleus small or large? Were these jets stable vents or short-lived bursts? Was the strange sunward structure in early images a trick of perspective or a sign of something more deliberate? This is where those Mars orbit images stop being a curiosity and start looking like a missing piece of evidence. If you are an astronomer setting up follow-up campaigns, you need to know what this thing actually looks like. Should you plan for a compact core or a fractured swarm? Do you point your instruments to catch a single dominant jet or a whole bouquet of outflows? With each day of silence, the window to make those decisions shrinks because the object is racing away from the Sun, growing fainter and harder to study. Harvard astrophysicist Avi Loeb has been blunt about this. He has argued that science should not be held hostage by bureaucracy and that time-sensitive data about a unique visitor from another star belong in the hands of the global scientific community. His point is simple and hard to argue with. Every week of delay is a week lost, not in some abstract sense, but in concrete. Observation time. Telescopes have schedules. Nights are booked months in advance. If teams do not know what the Mars images reveal, they are guessing where to invest their limited hours under dark skies. Now place yourself in the role of a curious outsider watching this unfold. On one side, you see a steady flow of ordinary content: Mars landscapes, meteorological updates, routine missions. On the other side, you see a single object tagged with special handling. A note about a shutdown that has already ended. A silence that stretches past 40 days. Nobody has to whisper the word cover-up for the situation to feel off. When one dataset is treated like any other and another is placed behind a kind of soft curtain, your mind naturally starts to ask why. There are benign explanations. Maybe the images are harder to process than usual because the target is moving. Maybe there are internal debates about how to describe what the frames show. Maybe public affairs offices want to coordinate messaging with other agencies or international partners. Bureaucracies often move slowly, even when no one is hiding anything, yet the timing still matters. 3I Atlas is not a static crater on Mars. It is a changing, active object whose behavior is the whole point of the story. Delay does not just frustrate curiosity, it erases opportunity. The real tension comes from that contrast. On one side, an interstellar visitor that might be reshaping how we think about comets, probes, and the space between stars. On the other side, a file sitting on a server, waiting for a signature or a cleared inbox. When the universe sends you something this rare, you do not want the biggest obstacle to understanding it to be a paperwork bottleneck. You want open data, fast analysis, and a global swarm of minds digging into the details while the trail is still fresh. Right now, we do not have that. We have hints and partial views, and a glaring blind spot exactly where the sharpest images should. That is why the silence is so loud. It is not that someone must be hiding something dramatic. It is that no one seems in a hurry to prove otherwise. And as 3I Atlas drifts farther away, that lack of urgency becomes its own kind of answer, one that tells us as much about our institutions as it does about the visitor itself. To see why 3I Atlas matters so much, we have to zoom out and look at the tiny club it belongs to. In all of human history, we have only confirmed 3 visitors from other star systems. The first was Oumuamua in 2017. The second was 2I Borisov in 2019. The third is this object we are following now. 3 bodies in total. 3 radically different personalities. When Oumuamua first streaked through the inner solar system, it was a shock. It was small, faint, and already on its way out by the time we noticed it. Its shape looked elongated, maybe like a cigar, maybe like a flattened chip, depending on whose reconstruction you read. It tumbled end over end. It showed a tiny but stubborn deviation from the path gravity alone would dictate. That deviation sparked endless arguments. Was it a comet with invisible gas? A nitrogen iceberg chipped off a distant world? A fragment of something more artificial? No consensus, just a long shadow of mystery. Then came 2I Borisov, and astronomers almost sighed with relief. Here, finally, was an interstellar object that played by the rules. It had a classic coma, a tail pushed away from the sun, and spectra that looked like a normal icy comet. It behaved the way textbooks said a comet should behave. In a way, Borisov was comforting. It told us that other planetary systems can make the same kind of frozen debris ours does. Strange, elongated Oumuamua could be the oddball, the exception. 3I Atlas does not fit into either of those boxes. It is not a tiny, faint shard that slips past detection until it is already leaving. It is not a simple comet clone, politely, venting gas and dust in one direction. From the moment it was discovered on the 1st of July 2025 by the Atlas Survey telescope in Chile, its orbit told us one thing clearly. This object does not belong to the Sunday. The orbit is hyperbolic, a one-way track. It came from interstellar space, it will leave to interstellar space, and we get one pass to understand it. So far, every time we have pointed a serious instrument at 3I Atlas, it has given us more questions than answers. Early images showed not just a normal antisolar tail, but a strange structure pointing almost back toward the Sunday. That was our first hint that this visitor might not be satisfied with simple behavior. As it moved inward, astronomers watched for the usual signs: more dust, more gas, maybe fragmentation, as the heat built up. Instead, they began to notice more complex geometry: jets, halo, structure that seemed to resist easy categorization. Think about what that means for scientists who lived through the debates over Oumuamua and Borisov. The first object was too weird and too early. The second object was exactly what theory predicted. You could imagine those two forming a neat narrative. The universe is full of icy bits. One was an odd fragment caught at a bad viewing angle. The other was normal. Story over. Then this new body shows up, and instead of smoothing the pattern, it breaks it open. The orbit alone already makes it important. When you calculate the incoming path of 3I Atlas, you find that it is not wildly tilted compared to the planets. It slices through our solar system on a path that stays close to the plane where Earth and Mars and the other major worlds orbit. That is not impossible for a natural object, but it is statistically surprising. If interstellar debris came in from random directions, you would expect most visitors to arrive on paths that cut steeply across that plane. 3I Atlas is far better aligned than randomness would suggest. Combine that neat alignment with its timing and things get more interesting. It arrives at a moment in history when we have powerful survey telescopes scanning the sky, radio arrays listening across wide bands, orbiters parked around Mars with cameras sharp enough to zoom in on a rover. 1,000 years ago, this thing would have blazed past unnoticed. 100 years ago, we might have noticed a fuzzy comet and nothing more. Today, we have the tools to dissect its every move, every jet, every spectral line, if we use them. This is also why its growing weirdness matters. With each new data set, the universe could have reassured us. Ground-based images after perihelion could have shown a standard comet tail and fading activity. Instead, they show multiple jets pointing in different directions, including back toward the sun, and a glowing envelope extending roughly 500,000 kilometers into space. Radio observations could have come up empty, leaving 3I Atlas as a purely optical story. Instead, they detect hydroxyl emission at a frequency that has decades of history in searches for technology. Orbital tracking could have shown a simple gravitational path. Instead, analysts report subtle, non-gravitational accelerations. This is not how ordinary comets calm a field down. This is how they light it on fire. 3I Atlas keeps landing exactly on the line where natural explanations are possible, but strained. Yes, sunward structures can appear through geometry and rotation, but the pattern here is complex. Yes, non-gravitational acceleration can result from gas venting, but the timing and magnitude demand careful modeling. Yes, hydroxyl at those radio frequencies is expected from water ice, but the context brings techno-signature conversations back into the room. The deeper frustration is that, unlike with Oumuamua, we are not limited purely by distance and timing. The tools to decide between simple and extraordinary are already pointed its way. High-resolution cameras in Mars orbit, sensitive spectrographs on Earth, radio arrays with the right frequency coverage. The object itself is performing in the spotlight. The problem is not a lack of stage. It is a lack of access to the best seats, and in some cases, a curtain pulled halfway across the view. In a sense, 3I Atlas has become a mirror for us, as much as a mystery in itself. It is testing not only our theories of how interstellar ice and rock behave, but also our willingness to confront anomalies honestly. We can lean on the comfort of natural variation and write every oddity off as a rare but harmless quirk. Or we can accept that this visitor refuses to be normal and let that discomfort push us to gather better data, ask sharper questions, and be open to answers we did not expect. When people talk about 3I Atlas, the first thing they often mention is the radio signal or the hidden images from Mars orbit. Yet some of the most unsettling clues are right in front of us in simple pictures. To understand why scientists keep staring at this thing in disbelief, we need to look carefully at its tail, because the tail is where the physics starts to break character. Start with what is supposed to happen. A comet is basically a dirty snowball. Far from the sun, it looks like a dark lump of ice and rock. As it moves inward, sunlight warms the surface. Ice turns directly into gas in a process called sublimation. That gas escapes from the nucleus and drags dust with it, forming a fuzzy atmosphere called the coma and a long, pale streamer we call the tail. The key rule is simple. Solar radiation and the solar wind push this material away from the sunday. No matter which way the comet is moving, the tail points anti-solar. You can imagine it like a cosmic weather vane. The nucleus is the pole. The tail is the flag. The wind of photons and charged particles always blows outward, so the flag always points away from the star. We have seen this thousands of times. Different comets, different orbits, same basic behavior. That is why every astronomer's eyebrows went up when the Hubble Space Telescope imaged 3I Atlas in late July and saw a structure that seemed to be pointing the wrong way. In that observation, the telescope had a nearly edge-on view of the object. From Hubble's vantage point, the line from the Sun to 3I Atlas was only about 10 degrees off the viewing direction. That is about as close as you can get to looking straight along the beam of sunlight. In those conditions, if there is material extending along the orbital plane, you see it clearly as a narrow spike. What Hubble recorded was a bright structure reaching sunward, an anti-tail that did not look like a faint illusion but like a physical feature. Now, to be fair, anti-tails are not unheard of. With the right geometry, dust left behind in a comet's orbit can appear to stretch toward the Sun simply because of perspective. It is like standing on train tracks and watching the rails seem to converge in the distance, even though they are parallel. For many comets, that explanation is enough. You do a bit of orbital modeling, you show that the dust sheet and the viewpoint line up in a particular way, and the weird-looking tail becomes a visual trick. Case closed. 3I Atlas did not make things that easy. That Hubble anti-tail was only the opening act. After perihelion, when the object swung around the Sun and began to move back outward, a different set of observatories picked up the story. On the 9th of November, a team of observers released an image that froze the community for a moment. The comet was no longer just a nucleus with a single odd spike. It was surrounded by a vast, glowing halo roughly 500,000 kilometers across, with at least 7 distinct jets lancing out from the core. Some of those jets pointed away from the Sun as expected. Others pointed back toward it. 2 days later, another team shared their own deep exposure. The details differed, but the message was the same. Multiple bright structures, some sunward, some anti-solar, arranged in a pattern that looked almost organized. Not a simple smooth tail, but a 3-dimensional skeleton of beams and fans. Meanwhile, the Virtual Telescope project, which had been tracking 3I Atlas night after night, released a time sequence showing the entire system growing. The halo swelled, the main tail lengthened. The individual jets stayed surprisingly crisp. This is where simple perspective arguments start to creak. Yes, geometry can make one dust feature look strange from one viewpoint. What we are seeing here is something else. Multiple independent teams, using different telescopes, at different times, and from different locations, are all recording a complex lattice of jets that keep their identities over days. Some of those jets point along directions that, by all expectations, should be hostile to loose dust. Sunward structures are not supposed to thrive under a constant blast of radiation. Think of a normal comet as an ice cube on a hot plate. As it warms, water runs off in rivulets that change and merge and break up. The flow is messy. It does not pick 7 perfectly spaced directions and stick to them. Now imagine that instead of a chaotic trickle, your ice cube produced 7 clean, narrow streams that held their shape as they arced away. That is closer to what 3I Atlas seems to be doing. Another odd detail is how focused those jets appear. In many comets, individual jets start narrow near the surface, but quickly fan out into a diffuse plume that blends into the coma and tail. With 3I Atlas, some of the structures remain tight and beam-like over enormous distances, well over 1 million kilometers in some estimates. That level of focus suggests that either the vents on the surface are very sharply defined, or that whatever is producing the jets is doing so in a remarkably disciplined way. Astronomers do have natural models to reach for. One is that the nucleus is spinning with specific active regions. As it rotates, sunlight hits particular patches, each acting like a nozzle. If those vents are located in certain latitudes and longitudes, and if the spin axis is tilted just right, you can get jets that appear in a structured arrangement. Combine that with the line of sight from Earth and you can, in principle, produce complex shapes. It is a lot of ifs, but nature can be baroque when you give it enough parameters. Still, the more this object is imaged, the more the pattern feels like a signature rather than an accident. The sunward jets keep showing up, the number of distinct beams stays high. The halo keeps growing while the inner geometry stays oddly neat. Each observation delivers the same underlying message. This is not a simple snowball shedding gas in a random spray. It is a system of flows that behaves as if there is a plan, whether that plan is written by physics on a strangely carved surface or by something with intentions. For now, the images alone cannot tell us which story is true. What they do is narrow the field. Easy explanations are gone. The anti-tail is not just a trick of the eye from one telescope on one night. The jets are not simple gusts that vanish with the next spin of the nucleus. We are left with a visitor whose tail keeps pointing in directions that demand justification and whose evolving shape keeps reminding us that sometimes the strangest clues are literally trailing behind. At first glance, jets blasting out of a comet sound perfectly ordinary. Give an icy rock enough sunlight and it will respond by venting gas. That is exactly what a comet is supposed to do. The trouble with 3I Atlas is not that it has jets. The trouble is how those jets behave and what they might be telling us about how this object moves. At some point, you have to ask a simple, unsettling question. Are we watching natural geysers or something closer to engine exhaust? Start with the standard picture. A comet. Nucleus warms up as it nears the Sunday ice. Inside, the surface layers turns directly into gas. That gas pushes its way out through cracks and porous regions, carrying dust and larger grains with it. The flow speeds are not mysterious. They are set by basic thermodynamics. For typical comet ices near the orbit of Mars, gas escapes at a few hundred meters per second. That is fast enough to loft material into space and to carve visible jets, but it is not extreme. Because those jets act like tiny rockets, they do more than paint pretty structures. They also nudge the comet itself. Every molecule that flies off carries away momentum. The nucleus recoils in the opposite direction. Over weeks and months, that gentle push can add up to a measurable change in the orbit. Astronomers call this non-gravitational acceleration. It has been seen in many comets. It is one reason orbital models include outgassing forces as well as the pull of the sun and planets. So, when early orbit fits 3I Atlas started to show small discrepancies, no one panicked. A little non-gravitational acceleration around perihelion could fit comfortably inside the normal comet story. The problem is that with this object, normal assumptions keep colliding with other oddities. The jets do not look like short-lived puffs. They look stable and sharply focused. The geometry is complex, with multiple beams in multiple directions, some of them sunward. The halo is huge. The whole system seems more organized than chaotic. If you wanted to decide whether these jets are truly ordinary vents, you would reach for spectroscopy. That is the art of spreading light out into its component colors and reading the fingerprints. When gas moves toward or away from us, its spectral lines shift slightly in frequency. From that shift, you can calculate velocity. For a natural comet, you expect most gas to be moving at those few hundred meters per second, set by sublimation physics. Maybe a bit more from additional processes, but not dramatically higher. Now imagine a different scenario. Instead of random ice pockets, an internal system is deliberately directing streams of material out of carefully placed nozzles. Those streams are being used not just to relieve pressure, but to steer. In that case, the exhaust may move at much higher speeds, several kilometers per second. That is an order of magnitude jump. It is the difference between a gentle leak and a purposeful thruster. On paper, the way to tell the difference is straightforward. Measure the velocities of the gas in those jets with enough precision and see which regime you are in. In practice, it is not that easy. You need bright, narrow spectral lines from molecules in the jets. You need large telescopes with sensitive instruments tuned to the relevant wavelengths. You need enough observation time while the object is still bright. And you need clean geometry so you can separate motion along the line of sight from sideways motion across the sky. None of this is impossible. It is the sort of challenge astronomers deal with all the time. What makes it urgent here is the clock. 3I Atlas is moving away. Every week the signals get weaker. Meanwhile, the images we already have keep pushing us toward that uncomfortable fork between natural and engineered. A natural model can explain stable jets if the surface is carved in the right way. Imagine deep vents that collimate the gas like pipes, turning messy boiling into narrow streams. Combine that with a specific spin axis, and you can get repeated patterns as the nucleus rotates. The sunward jets could come from vents that happen to face the sun at certain phases, with gas bursting out strongly enough to overcome radiation pressure for a while. The alternative is to picture an object with internal tanks, valves, and guidance. There, the sunward jets are not accidents of rotation, they are maneuvers. Use the sun as a spotlight and a power source. Heat stored volatiles. Vent. Put them in directions that change trajectory, while everyone watching can still shrug and say Comet. Any anomalous acceleration that shows up in orbit fits get filed under outgassing. Any jets caught in images are chalked up to exotic but natural behavior. It is a clever camouflage strategy, if such a thing exists. Right now, both stories can be made to fit. The non-gravitational acceleration observed near perihelion is real. The question is whether it can be fully explained by reasonable outgassing models that match the observed jets, or whether there is leftover acceleration that refuses to go away. The focused beams are real. The question is whether surface physics can keep them that tight over millions of kilometers, or whether we are underestimating how deliberate they might be. This brings us back to those hidden high-resolution frames from Mars orbit. A side view of the jets could show whether they widen and bend like normal gas flows or stay unnaturally straight. It could, to reveal if the jets originate from a single solid nucleus or from multiple pieces arranged in some pattern. Combine that with spectroscopic velocities and precise orbit tracking, and the balance between natural vent and engine exhaust would tilt one way or the other. Science is built to handle this kind of fork in the road. You set up competing models, you make predictions, you gather data that discriminate between them. What makes the 3i Atlas case frustrating is not that we lack ideas. It is that some of the most powerful tools are either late, locked up, or still being processed behind closed doors, while the object itself is flying out of reach. The universe has handed us a test case for how to tell Comet from craft. The physics is ready. The instruments are ready. The main question now is whether we will see enough, soon enough, to decide which story these jets are really telling. So far, our story has lived mostly in visible light. Strange tales, symmetric jets, missing, images. Then a different kind of clue arrived, not as a picture, but as a whisper in radio waves. While telescopes watched 3i Atlas gleam near the sun, an array of dishes in South Africa was listening, and what it heard dropped this object into one of the strangest neighborhoods in the entire electromagnetic spectrum. On the 24th of October, 5 days before perihelion, the Meerkat radio telescope pointed at 3i Atlas. Meerkat is not one dish. It is a coordinated swarm of antennas spread across the landscape, acting like a single giant ear. It is built to pick up faint radio emission from distant galaxies and cosmic gas clouds. On that day, in the direction of our interstellar visitor, it picked up clear signatures of specific molecules. The frequencies sat around 1.66 gigahertz, exactly where hydroxyl radicals like to speak. Hydroxyl is a simple fragment, one oxygen atom bonded to one hydrogen atom. In comets, it is a daughter product of water ice. Sunlight and energetic particles break water apart, and some of those pieces radiate at very specific radio frequencies. So, if you take a normal comet, warm it up near the sun, and listen in the right band, you should hear these hydroxyl lines. That is why, on one level, the Meerkat detection is almost boring. It confirms that 3i Atlas has water ice, and that this ice is being destroyed and turned into gas as the object heats up. Yet the precise part of the spectrum where this happens is anything but boring. The hydroxyl lines sit at the high-frequency edge of a region radio astronomers nicknamed the waterhole. On the low side is the famous hydrogen line around 1.42 gigahertz. On the high side lie the hydroxyl features near 1.67 gigahertz. Between them is a relatively quiet band, free from many natural sources and atmospheric noise. For decades, researchers searching for technological civilizations have eyed this region as prime real estate for deliberate signals. Hydrogen and hydroxyl combine into water, and water is essential for life as we know it. Symbolically and practically, it is a natural hailing channel. That is why the history of this band includes legends. In the 1970s, the Big Ear Telescope in Ohio detected a strong, narrow, unexplained burst near the hydrogen line. The signal lasted a little over a minute, was never seen again, and was so startling that the astronomer who found it in the data circled it and wrote the word "wow" in the margin. To this day, no one can say for sure what it was. That event helped cement the idea that if anyone out there wanted to get our attention, the hydrogen and hydroxyl region would be a smart choice. Now roll the clock forward to 2025. An object from another star, already behaving strangely in visible light, suddenly lights up in hydroxyl emission right in the waterhole. It happens at exactly the time when solar heating is strongest, which matches the expectation for natural ice boiling off. It also happens at exactly the time when an artificial object could most easily hide its activity behind the same natural explanation. That coincidence does not prove anything, but it is hard to ignore. The Meerkat team reported that the hydroxyl signal was centrally concentrated. That is an important detail. It means the emission came from near the nucleus, rather than from a diffuse cloud spread far along the tail. In other words, the radio detection pins the action close to a compact core. This is true whether that core is a lump of ice and rock or something more engineered wrapped in a layer of volatile material. Either way, 3I Atlas is not just a ghostly dust cloud. It has a solid heart that is actively shedding molecules. Once again, we arrive at a fork where more data could push us one way or the other. Natural sublimation produces gas at characteristic velocities. Hydroxyl fragments born from water ice usually drift away at a few 100 meters per second. If you could measure the Doppler shift of the radio line precisely, you could map out that speed distribution. If instead you saw velocities many times higher, clustering around several kilometers per second, that would hint at a different mechanism, one more like a directed exhaust. The diagnostic is clear on paper. In practice, extracting those tiny shifts from a faint signal is demanding work. So far, only the basic detection has been announced in detail. The full velocity analysis is still described as in progress. That is scientifically normal for a brand new dataset. Yet, in the context of everything else around 3I Atlas, it adds to a pattern. The images from Mars orbit sit in a queue. Detailed spectroscopic work on the jets is ongoing but unpublished. Now, the richest information hidden in the hydroxyl line, the exact motion of the gas, is also somewhere in the pipeline. Meanwhile, the object itself is sliding away into the dark, its radio voice fading. There is another layer to this that makes researchers uneasy in a good way. If you were designing a probe to move through another solar system without drawing attention, you might wrap it in ice or porous rock, both as protection and camouflage. When you needed to maneuver, you could vent some of that material. To outside observers, it would look like Comet outgassing. The exhaust would naturally produce hydroxyl near the sun, and any radio emission from that process would fall right where comets are expected to glow. The perfect disguise is one that matches background physics so well that only very precise measurements reveal anything odd. This is why voices like Avi Loeb keep stressing the need for rigor without ridicule. The hydroxyl detection is entirely consistent with a normal interstellar comet. It is also compatible with a more exotic scenario in which a technological object is hiding in plain sight. Both possibilities live under the same data point. Both make clear predictions about gas velocities, line widths, and how the signal should evolve as the object moves away from the sunday. The way to choose between them is not to vote based on gut feeling, it is to measure. So the radio whisper from 3I Atlas does two things at once. It grounds the object in chemistry we understand and pulls it deeper into a region of the spectrum that has long been associated with the search for minds beyond Earth. It reminds us that natural and artificial can occupy the same frequencies, and that the difference lies not in where a signal appears, but in how it behaves when you look closely. If you are still with this story, if that kind of subtlety excites you rather than pushing you away, make sure you are subscribed and paying attention, because the real test of this detection will come when those finer details finally leave the notebooks and reach the wider world. If you want to know what something is made of, You do not treat it gently. You send it through fire. For comets, that trial by fire is perihelion, the moment when they swing closest to the sun and face the full fury of its heat and radiation. Many do not survive. They crack, fragment, or simply vanish into a smeared-out cloud of dust. 3I Atlas did something else. It went in as a strange but simple object and came out looking more alive than before. On the 29th of October, 3I Atlas reached its closest point to the Sun, just inside the orbit of Mars. That distance sounds comfortable compared to the scorched paths of some sun-grazing comets, yet the environment is brutal. The intensity of sunlight is far higher than near Earth. The surface temperature of any exposed ice jumps. Subsurface layers feel the stress as heat conducts inward. Tiny cracks widen. Weak regions fail. For a fragile, loosely held together body, this is exactly when things start to fall apart. We have watched that happen many times. Comet Shoemaker-Levy 9 was torn into a string of fragments by the gravity of Jupiter before crashing into the planet. Comet Ison brightened dramatically on its way toward a close solar passage, then disintegrated, leaving only a ghostly smear as it rounded the Sunday. Smaller comets that dive even closer often do not make it at all, burning out in coronagraph images as the last of their ice boils away. The pattern is clear. Get too close with too little structural strength, and the star will win. 3I Atlas had every reason to follow that script. It was not just dealing with steady sunlight. The solar cycle is active, and coronal mass ejections have been blasting out through the inner system. These eruptions fling huge clouds of magnetized plasma into space. When that kind of storm sweeps across a comet, it can shred its tail, strip away gas, and hammer its magnetic environment. For a delicate object already under thermal and tidal stress, a strong solar storm is like a punch on top of a fever. Yet when 3I Atlas emerged from behind the sun in early November, it did not look like a patient barely clinging to life. It looked like something that had just switched on. Ground-based telescopes that picked it up again did not see a faint leftover core and a ragged trail. They saw a massive, bright halo extending roughly 500,000 kilometers from the nucleus. They saw multiple jets, at least 7 in some analyses, fanning out in different directions. They saw a tail that was not fading, but growing, lengthening visibly from night to night. In other words, the object went through its closest approach and came out more active and more structured than it went in. That is not what we expect from a simple pile of ice and dust barely held together by its own gravity. When comets are pushed past their limits, they usually become less coherent, not more. They fragment into smaller pieces that drift apart. Their activity spreads out into a messy cloud. Whatever order existed is erased by stress. 3I Atlas seems to have taken that stress and used it to reveal a new level of organization. There are natural ways to frame this transformation. Before perihelion, much of the heat from the sun is absorbed in the outer insulating layers. The interior remains cold and quiet. As the object spends more time near the sun, that thermal wave penetrates deeper. Subsurface pockets of volatile material that had never seen starlight before suddenly warm up. Pressure builds under the crust. At perihelion, that pressure can finally punch through, opening new vents. Afterward, those vents gush gas and dust, feeding new jets and a larger halo. From this perspective, 3I Atlas did not magically become more complex. It simply woke up deeper layers of ice. Still, even in that natural picture, the result is remarkable. The object did not explode into 1,000 shards. It held together, strongly enough that these new vents behaved like nozzles on a single unified body. The halo wrapped around a coherent center. The jets emerged from what appears to be a compact nucleus, not a debris field. That suggests real structural integrity. Perhaps the nucleus is reinforced by rocky material or sintered crust that gives it a toughness beyond a fluffy snowball. Perhaps it formed in a region around its original star where ice and dust fused differently than they do here. Then there is the more provocative framing. If 3I Atlas is not just a natural body, then perihelion was not simply an ordeal, it was an opportunity, a planned maneuver. In that view, the object approached the sun on a carefully chosen trajectory, dipping close enough to harvest a gravitational assist while also using the intense heat to drive controlled outgassing. New jets did not just happen, they were activated. The transformation we see afterward is a mission phase change, the craft shifting from one mode to another as it enters a new leg of its journey. In that scenario, surviving perihelion intact and emerging more active is not surprising. It is the whole point. We design our own probes to endure extreme conditions. The Parker Solar Probe dives repeatedly through the Sun's outer atmosphere behind heat shields, its instruments tucked into safe corridors. Voyager and Pioneer were hardened against radiation belts. An interstellar machine could easily be built to tolerate a Mars-distant solar pass that would rip apart weaker rubble piles. Its structure might be metallic or composite, with an icy cloak serving as camouflage and propellant, not as primary bulk. Once again, both stories demand assumptions. The natural story assumes that an interstellar comet can have unusual strength, unusual layering, and an interior ready to erupt into complex jets once the right temperature threshold is reached. The artificial story assumes that technological civilizations exist, that they build probes, and that those probes might pass through our system wrapped in ice. Neither option is comfortable. One stretches our models of comet physics. The other stretches our sense of how alone we are. This is where those high-resolution images from Mars orbit become precious. A close look at the nucleus could tell us whether we are dealing with a single solid object or a cluster. It could reveal surface texture that hints at layered geology or engineered panels. It could show fractures, cliffs, or smooth facets, each carrying a different implication. Right now, we know that 3I Atlas went through fire and came out not just alive but transformed. What we do not know is whether that resilience belongs to a very unusual piece of nature or to something that was built to survive exactly this kind of starside trial. The universe has handed us a before and after snapshot in dynamical form, the same object, pre-perihelion and post-perihelion, behaving like two different characters, comet and something more, ice ball and performer. Until we see the finest details and combine them with careful measurements of motion and composition, we are left with a fact that is hard to dodge. 3I Atlas went through an experience that erases many comets from existence and responded by becoming more complex. Whatever it is, fragile is not the right word. If you were throwing darts at the solar system from deep space, you would expect most of them to miss the thin pancake where the planets orbit. Space is three-dimensional. There is no reason for random interstellar debris to arrive neatly lined up with the flat plane of our worlds. Yet 3I Atlas did exactly that. Its path through the inner system hugs that plane in a way that looks less like a wild dart and more like a carefully chosen lane. On paper, the orbit is hyperbolic. That means one thing clearly. This object is not bound to the Sunday. It came in from interstellar space and, unless something changes, it will leave again. When astronomers fit that orbit, they use dozens and then hundreds of position measurements taken over weeks. Early on, those measurements already showed the odd alignment. The object was not plunging in from a steep angle above or below the planetary plane. It was sliding along a track that sits surprisingly close to it. That is not impossible for a natural visitor. If the galaxy is full of drifting chunks thrown out of young planetary systems, some fraction will happen to pass through our backyard in tidy ways. But the statistics are not on that side. The volume of space above and below the planetary plane is vast compared to the thin slice our worlds occupy. Getting an interstellar object that sails right through that slice is like having a random car from another highway drop onto a specific exit ramp at exactly the right angle. It can happen. It is just not the default expectation. Now combine that geometry with timing. 3I Atlas arrives during an era when we have survey telescopes scanning the sky every clear night, planetary orbiters carrying precision cameras and radio arrays listening across broad bands. It threads a path that brings it close enough to Mars for HiRISE to image it, close enough to our line of sight for Hubble and ground-based telescopes to catch its strange tails, and close enough to the Sun for a dramatic perihelion passage without disintegration. If you were planning a reconnaissance tour through a foreign solar system, you could do much worse. The orbit around perihelion is where things get even more interesting. Any object falling toward the Sun will naturally speed up, swing around, and head back out. That is gravity doing its simple, reliable work. Space agencies have learned to use this effect to their advantage. They send spacecraft past planets to steal a little orbital energy, changing the craft's speed and direction without burning much fuel. This is a gravitational assist, and we have used it with Venus, Earth, Jupiter, and other worlds. In principle, the same trick works with a star. Dip in close enough, and you can tilt and boost your path with exquisite efficiency. For a natural comet, the exact details of that swing are set by its initial trajectory and the shape of the sun's gravity field. At most, jets of outgassing can add a gentle nudge, a small non-gravitational acceleration that slightly warps the path. For an engineered object, the story could be very different. A small amount of directed thrust near perihelion, timed to coincide with the strongest solar gravity, could produce a meaningful course correction while still looking like ordinary outgassing to outside observers. This is why precision tracking matters. Astronomers compute a purely gravitational orbit for 3I Atlas and then compare it with what their telescopes actually see. Any systematic differences show up as residuals. When those residuals cannot be removed by better measurements or more careful accounting for outgassing, you know something is pushing the object in an unexpected way. Reports of non-gravitational acceleration near perihelion are already on the table. The question is whether they can be fully explained by plausible jets, or whether there is a leftover push that refuses to vanish. Imagine plotting the path of 3I Atlas before perihelion and projecting where it should go afterward. If the object were a passive rock, the post-perihelion trajectory would lie almost exactly along that predicted curve. If it were an active comet, you would allow for small deviations pointing roughly away from regions where gas vents strongly. If it were an actively steered craft hiding behind comet behavior, you might see a cleaner, more decisive change, a subtle bend that lines up with a long-term plan rather than random vent locations. In practice, separating these scenarios requires astrometric accuracy down to tiny fractions of an arc-second and careful modeling of every known force. There is another clue hidden in the inclination. An interstellar object captured by pure chance into a bound orbit around the Sun would require a very specific combination of incoming speed and impact parameter. It is like threading a cosmic needle. Add a bit of thrust at the right moment, however, and that capture becomes much easier. If 3I Atlas were using perihelion as a braking and steering maneuver, it could trade some of its incoming energy for a long tour through the inner system, perhaps even looping around in a way that keeps it near the planetary plane for a very long time. That possibility is speculative, but it follows the same physics we use for our own probes. Right now, the official orbit solutions for 3I Atlas still classify it as an unbound visitor. No one has announced a clear capture into a long-term solar orbit. That is important. Extraordinary claims require solid evidence, and we do not have that yet. What we do have are hints that the trajectory is not as boring as a simple falling rock. Non-gravitational terms are needed to make the fits-match observations. Those terms may turn out to be fully consistent with natural jets once all the data are in, or they may not. Once again, the missing or delayed datasets sit at the heart of the puzzle. High-resolution images from Mars' orbit could show the exact orientation of jets at the moment when the orbit began to deviate. Detailed spectroscopy of those jets could reveal whether the gas speeds match normal sublimation or something more forceful. Continued tracking as 3I Atlas recedes will tighten the orbit solution and show whether any lingering anomalies remain when the comet is far from the Sun and relatively quiet. Until then, we are left with an orbit that looks suspiciously tidy in some ways and unsettled in others. A visitor from another star glides in along the same flat plane our planets share, swings past the Sun with just the right distance to survive and transform, and now heads back out along a path that might carry subtle fingerprints of steering. Maybe this is what rare but natural interstellar comets look like when we finally see them up close. Maybe this is our first prolonged glimpse of something that is not just falling toward the Sun, but navigating. The only honest answer for now is that the sky has given us a trajectory worth watching in painful detail, and we will either confirm that it is merely neat or learn that it is something far more deliberate. By now, you have probably noticed something odd about this story. The sky keeps giving us more information, while the institutions built to study the sky keep giving us reasons to wait. 3. iAtlas is not just stressing our ideas about comets and interstellar visitors, it is also stress testing how we handle discovery in real time. On one side stands the scientific method with its demand for open data and shared scrutiny. On the other side stands a culture of caution that reaches for pause buttons exactly when curiosity should be hitting play. Take the HiRISE images sitting on that server. No one disputes that they exist. The observing plan was public. The spacecraft executed it. Mars Reconnaissance Orbiter pointed its sharpest eye away from Mars and locked onto an interstellar visitor passing nearly alongside it. Under normal circumstances, those frames would move through a pipeline that has been refined over years. Calibration, basic processing, quick release. Instead, they hit a flag that says NASA-wide news, and everything stopped during the federal shutdown. That pause came with a convenient explanation. Official news channels were frozen, so anything labeled as major news needed to wait. That at least sounded like a rule, even if it was frustrating. Then the shutdown ended. Other announcements flowed again. Press releases about launches, hurricanes, and Mars geology went out. Yet the 3 iAtlas images remained behind the curtain, still tagged as something that needed special handling. It started to look less like a temporary hiccup and more like a choice. Inside an agency like NASA, choices often move slowly. Data can pass through science teams, media offices, legal reviews, and coordination calls with other institutions. Nobody wants to be the person who misphrases a complex result and sparks a wave of wild headlines. In that sense, the caution is understandable. When you are sitting on data about an object that already has people whispering about aliens and cover-ups, you might feel a strong urge to get every sentence perfect before you let anything out. The problem is that the universe does not wait for internal memos. 3i Atlas is not a static rock on Mars. It is an active object that changes week by week. The window for high-precision observations is closing as it recedes from the Sunday. Every day those Mars orbit frames stay private is a day when telescope time is being scheduled in the dark, when models are being built on incomplete information, and when confusion fills the space that data should occupy. Silence has a cost measured in lost opportunity. You can see the contrast if you look at other recent breakthroughs. When the first detection of gravitational waves happened, the team did keep the data internal until they were sure. But once the result was solid, the waveforms, the methods, and the analysis were shared widely. Other groups could test the pipeline, check the signal, and build on it. The same has been true for many exoplanet discoveries and cosmic surveys. The pattern there is clear. When information flows, science accelerates. Independent eyes catch errors, refine models, and sometimes see possibilities the original team missed. With 3i Atlas, we are watching the opposite pattern. Evidence of non-gravitational acceleration appears, and the details drift out in fragments. Ground-based images of bizarre jets arrive from scattered teams, while the best geometric views sit unpublished. A clear radio detection in the waterhole is announced, but the full velocity analysis remains somewhere in the future. Each piece that could strongly favor one model over another seems to move through a narrow, slow corridor instead of into the wide-open arena where many minds can attack it at once. This is not simply about impatience, it is about trust. When an agency that is usually proud to share its images suddenly becomes hesitant around one particular target, people notice. The delay might be completely innocent, the product of overloaded staff and complicated coordination, yet, from the outside, it feels like selective opacity. One object is treated like routine business, another like sensitive material. That double standard is what feeds speculation. Where there is a clear process, conspiracy theories struggle. Where there is a visible gap, they thrive. Avi Loeb and others have argued that this is exactly the wrong way to handle potential breakthrough data. If there is any chance that an object represents an entirely new class of interstellar comet, or even a piece of technology, the best defense against bad ideas is an aggressive offense of good science. Release the images, publish the spectra, let dozens of independent groups try to fit the orbit, model the jets, and interpret the radio lines. If the weirdness dissolves under that kind of pressure, great. If some anomalies remain, At least we can be confident they are real. There is also a deeper cultural question hiding here. For most of the space age, the public learned about discoveries through official statements. A mission team would study a result behind closed doors, then present a finished story on a stage or in a glossy release. That model made some sense when data was scarce and instruments were few. Today, we are in a different world. Amateurs can download raw images, run their own analyses, and share results instantly. Citizen scientists help catalog exoplanets and distant galaxies. In that world, trying to tightly script how a discovery unfolds can backfire. 3I Atlas sits right at that crossroads. It is being watched by professionals and amateurs, by mainstream astronomers and techno-signature hunters, by curious laypeople who have never heard of hyperbolic excess velocity but know what a cover-up feels like. The choice is not between chaos and control. It is between inviting the world into the process or leaving them outside to guess. The object itself is already strange enough. Adding layers of avoidable secrecy only makes the story harder to navigate. The irony is that no matter what 3I Atlas turns out to be, the way we handle it will set a precedent. If it is a natural comet with extreme but explainable behavior, the current delays will have wasted precious time and undermined confidence for no gain. If it is something more exotic, the delays will have slowed down our ability to recognize it and prepare for whatever that recognition implies. In both cases, transparency would have served us better. So when we compare science and silence in this case, we are not pitting reason against irrationality. We are weighing two different instincts inside the same community. One instinct says, be careful, be slow, minimize embarrassment. The other says, be open, be fast, let many eyes sharpen the truth. 3I Atlas is forcing us to choose which instinct we want to guide us the next time a visitor from the stars does something we do not expect. Because there will be a next time, and how we respond now will echo into that future encounter. Step back for a moment and forget the technical details. Forget the exact frequency of the radio line and the pixel scale of the Mars camera. Ask a simpler question. What does it mean that we are even having this conversation? 3 times in less than a decade, our instruments have caught objects that came from somewhere beyond the Sun's family and crossed our path. Each one has behaved like it has a different story to tell. Oumuamua was the wake-up call. It arrived fast, left faster, and refused to fit neatly into the boxes we had prepared. Not quite a comet, not quite an asteroid, with a shape and rotation that stretched our models. It bent away from a pure gravitational path by a tiny but stubborn amount. Some argued for hidden ice vents, others for exotic chunks of nitrogen or fractal dust. A few dared to suggest something more engineered. In the end, it left before we could settle the argument, like a stranger who walks through a room, drops a riddle, and vanishes. 2I Borisov felt like a relief. Here was an interstellar object that looked familiar. It had a coma, a tail, and a spectrum that matched ordinary icy bodies. It was still special because it came from another star, but it did not bend the rules. Many scientists hoped that as we found more of these visitors, most would resemble Borisov. Oumuamua could then be written off as the odd one out, a strange shard with an unlucky viewing geometry. The universe would be diverse, yes, yet fundamentally comforting. Then 3I Atlas showed up and shattered that hope of an easy pattern. It is more active than Oumuamua and more complex than Borisov. It sprouts anti-tails and sunward jets. It shrugs off perihelion and a solar storm and emerges more structured than before. It emits natural hydroxyl signals in a region of the radio spectrum that has long been tied to the search for technology. Its trajectory hugs the planetary plane in a way that feels suspiciously neat for pure chance. It is not just a new data point. It is a challenge. One way to read this is simple. Nature is more inventive than we thought. When you start sampling debris from many different planetary systems, you should expect surprises. Some chunks will be fluffy and fragile. Others will be dense and strong. Some will carry ordinary ice. Others will have exotic chemistry or layered crusts that vent in strange ways. In that story, 3I Atlas is a wild but natural comet. It is stretching our models, forcing us to rethink how interstellar ices form and fracture, yet still playing by unconscious physics. The other way to read it is more unsettling. If technological civilizations exist elsewhere in the galaxy, it would be astonishing if none of them ever launched probes into interstellar space. We have already sent several of our own machines on escape paths from the Sun, using chemical rockets and gravitational assists. Give another civilization a few million years of head start, and the tools they could build become almost unimaginable. The galaxy is old and wide. If anyone has ever seeded it with autonomous probes, some of those machines could be passing through right now. This is the heart of what people call the Fermi paradox. Given the age and size of the galaxy, and the apparent abundance of planets, it seems likely that life and intelligence should have arisen many times. If that is true, where is everybody? Why do we not see obvious megastructures or constant radio chatter? One answer is that we truly are alone, or nearly so. Another is that technological life tends to burn out quickly. A third is that the universe is full of activity, but most of it is subtle, cautious, or simply not aimed at us. Interstellar visitors like 3i Atlas force that abstract puzzle into a concrete form. Here is an object we can point at and say with confidence, this came from another star. It is doing things that are hard to explain cleanly with our current Comet playbook. It offers two broad classes of explanation. Either it is a natural but extreme example of alien geology, or it is an artifact of alien technology cloaked in that geology. Both possibilities are profound. Both are worth testing as ruthlessly as we can. If it is natural, then the lesson is that the galaxy's scrapyard is stranger than expected. That is good news for science. It means every future interstellar visitor will carry new physics and chemistry lessons. It means that by studying these bodies, we can learn how planets form under different suns and how common the ingredients for life might be. 3i Atlas would become the flagship example of how diverse comets can be when you zoom out from one solar system to many. If it is artificial, then the implications are almost beyond imagination. It would mean we are not the first to cross the interstellar threshold. It would mean another civilization has mastered long-duration travel across the gulfs between stars. It would mean the galaxy contains not just natural relics but designed machines, some of which might have been operating for timespans longer than human history. That realization would change everything about how we see ourselves. Our worries and achievements would suddenly sit inside a much larger story. Either way, the right response is the same: curiosity, rigor, and humility. We need to admit that we do not yet know which story 3i Atlas belongs to. We need to gather every bit of data we can, from hidden Mars images to faint radio lines, and attack them with open minds. We need to build a culture where scientists can say the words interstellar technology without being dismissed, while also insisting that extraordinary claims pass brutal tests. We are at the beginning of this era, not the end. New observatories will soon scan the sky with unprecedented sensitivity. They will find many more interstellar objects. Some will be boring. Some will be beautiful. A few may be as baffling as this one. The meaning of 3i Atlas for us might not be its final verdict at all. It might be the way it trains us to investigate the next visitor, and the one after that, with sharper tools and braver questions. The universe is handing us messengers from other stars. What those messengers are matters. How we choose to listen to them matters even more. Picture where we are right now. An object from another star is slipping back into the dark, taking its secrets with it. We have images that have not been shared, measurements still being processed, and models waiting for the last missing pieces. We also have a choice. What we do next will say as much about us as any final answer about 3i Atlas ever could. It is easy to fall into two comfortable extremes. One is to shrug and say it is only a comet, nothing to see, move on. The other is to leap straight to the most dramatic story and declare that it must be a probe, a machine, a sign. Both responses let us off the hook. One avoids the hard work of investigation, the other skips the discipline of proof. The universe deserves better than either, so do we. The honest position is the most demanding one. We admit that the data are incomplete and that the object is strange. We also admit that nature is incredibly inventive and that we have been surprised before. Then we commit to doing the slow, careful work of turning mystery into understanding. That means pushing for the release of every relevant observation, even when it is messy, even when it might undercut a dramatic narrative that people have already grown attached to. Start with the practical steps. Those HiRISE images around perihelion need to see daylight, raw if necessary, calibrated if possible. Once they are public, teams all over the world can examine the geometry of the jets, the size of the nucleus, and the structure of any halos or fragments. That takes the burden off a single group and turns a bottleneck into 100 parallel paths. The same goes for the detailed spectra and radio data. The more minds on the problem, the faster bad ideas die and good ones sharpen. Next comes the tracking. 3I, Atlas is fading, but it is not gone. Continued measurement of its position can tighten the orbit and reveal whether any unexplained acceleration remains once the jets quiet down. If the non-gravitational terms shrink away as activity falls, that supports the natural comet model. If they persist in ways that ordinary venting cannot explain, that will be a very different conversation. Either way, the key is to follow the evidence as far as it will go. Beyond this single object, we have a wider horizon to look toward. New survey telescopes will soon scan the sky deeply and frequently enough to find many more interstellar visitors. We will not be limited to 3 strange examples. We will have a growing catalogue. In that catalogue, 3I Atlas may end up as a rare outlier, a 1 in 1,000 comet with extreme behavior. Or it may turn out to be the first of a recognizable class, objects whose orbits and activity hint at something more than frozen rock. We cannot know yet. That uncertainty is not a failure. It is an invitation. There is also a cultural shift underway. For a long time, even mentioning extraterrestrial technology in a serious scientific context risked your reputation. Now, projects dedicated to techno-signatures are treated as valid research. Astronomers can openly discuss the possibility that some interstellar objects might be artificial without being pushed to the fringe. 3I Atlas is accelerating that shift. It is forcing us to build tools that can tell comet from craft in a principled way, not by gut feeling. That is the deeper legacy this visitor might leave. Even if every strange feature eventually finds a natural explanation, the process of ruling out the technological option will have refined our methods. We will have better models of outgassing, better handling of non-gravitational forces, better strategies for rapid data sharing when something truly weird appears. And if one day an object fails every natural test and passes the ones we would expect from a machine, we will be ready to recognize it with clear eyes rather than shock. Of course, there is a more personal side to all of this. Stories like 3I Atlas remind us that we are living at an extraordinary moment. For almost all of human history, the idea of witnessing a visitor from another star was pure myth. Now, it is a notification on a phone, a new preprint on a server, a set of pixels on a screen. We get to be the generation that learns how to read those pixels not just as pretty pictures, but as messages from the wider galaxy, whether those messages are written by geology or by minds. So what ending do we choose for this part of the story? We can let frustration harden into cynicism and assume that every delay hides something sinister. We can let excitement drift into fantasy and stop demanding evidence. Or we can do something harder and more useful. We can push for transparency, support the instruments and teams that gather the data, stay curious enough to keep asking sharp questions, and patient enough to wait for solid answers. We can treat 3I Atlas not as proof of anything yet, but as training for the next encounter, because there will be a next encounter. The universe is not done throwing mysteries our way. Whether the next visitor is a quiet shard of ice or something that truly breaks the rules, we will bring to it whatever habits we are forming now. Habits of secrecy or habits of openness. Habits of dismissal or habits of inquiry. In that sense, the most important thing 3I Atlas changes might not be our theories about comets at all. It might be us, and the way we choose to meet the unknown when it comes knocking from the dark between the stars.